So go to share my screen. And okay. Alright. So boleh nampak slide saya ya?
Boleh betul.
Okay, let's start. So, this is lecture number 4 of course SIG 3006. We are still on the topic of sequence stratigraphy. In the previous classes, we've learned that you get cycles in sea level, rise and fall. So sea level can only go up or down, but the magnitude might be different. Sometimes it goes up really high, sometimes it goes down really low, and so on, right? So it's in cycles. And this cycle in sea level, relative sea level, interacts with sediment, which is coming into the basin. So you can have variations in the sediment supply, and this interaction between relative sea level and sediment supply results in a pattern to your stratigraphy. Yeah, you get a certain kind of stratigraphic pattern. Right? And the overall pattern is this. You can divide your sea level cycle into different phases, right? First, during the low stand, you get progradation first, followed aggradation of your perisequence set. Then your shoreline goes backwards, and this is during the transgressive system strat. Okay? And this is a retrogradational perisequence set. And then this is followed by a slowing down of relative sea level during the high stand. So what happens is that you get an aggradational followed by progradational perisequence set, and then it is going to end with an erosional event, an unconformity. All right. So aggradation, progradation, degradation. So remember dia punya singkatan, remember the abbreviations. During the LST, it's going to be PA, progradation, aggradation. PST is going to be R, retrogradation, di belakang. And then during the HST, it's going to be aggrade, prograde, and degrade, APD. And then you have, going from LST, TST to HST, it's a single, a unit that we call a sequence. All right? And sequences are bounded by these surfaces called sequence boundaries. Now, we've looked at the general pattern inside the stratigraphy of a sequence, right? Now, today, I want to talk about the surfaces bounding the different system strats. Okay. Okay, so we want to look at these, what we call key stratigraphic surfaces. Ini permukaan-permukaan stratigrafi yang utama, kunci dia, right? And these surfaces, they bound the system strats. Dia jadi sempadan di antara system strats kita. So let's look at the key stratigraphic surfaces. Yeah? What kinds of stratigraphic surfaces do you have? The first one, the most basic one, is what we call a flooding surface. So remember, a flooding surface too is a boundary between perisequences, right? And it marks an abrupt shift in facies going from shallow to deep. So maybe you have a perisequence, right? And it is shallowing upwards, kan? Dia mencetek ke atas satu perisequence. And then it is when you have an abrupt flooding, tiba-tiba air naik amat cepat, so you get a very sharp surface. So that is a flooding surface. And they separate each individual perisequence. So if this was a perisequence, there's going to be a flooding surface at the top, another perisequence, another flooding surface, and so on. So the same here. One flooding surface, another one, another one, another one, and so on. All right. Now Now there are other kinds of stratigraphic surfaces. They are the key stratigraphic surfaces. So you have what we call a sequence boundary, and we've looked at sequence boundaries a little bit in the previous lecture. Then what we call transgressive surfaces. We usually abbreviate it, kita singkatkan jadi TS, transgressive surface. And we usually draw it as a blue line. Dijadikan dia garis biru biasanya bila kita lukis. A sequence boundary, we usually use the color red or orange, and the abbreviation is SD. A maximum flooding surface, ini salah, saya biasa, usually we use a green line to mark a maximum flooding surface. And we use the abbreviation MSS. So in this model here, you have a single sequence in the middle here. And it is bounded by two sequence boundaries, which are basically unconformities in this case. SB sini, SB sini. And then you have a TST, and it is above the LS, you have the TS, sorry, the transgressive surface, and it is marking the boundary between the LST and the TST. And then you have a green MFS here. You can trace it throughout the whole package of sediments here. And it marks the boundary between the TST and the HST. So let's look at these different key stratigraphic surfaces in more detail. Okay, first stratigraphic surface that we will look at is the sequence boundary. So what is a sequence boundary kan sebenarnya kan? Well, we know that it separates the different sequences. It is always underlying an LST. Okay, sentiasa di dasar low stand system tract. Okay. Now, so this is another cartoon of a shelf, right? And then you have a slope, right, and going to the basin here. So again, look at this. This line, which is red in color, is your sequence boundary. And the nature actually changes depending on where you are in the basin. On land, your sequence boundary is going to be a subaerial unconformity. It is an unconformity. A subaerial just means it is on land. It is under subaerial exposure. It's not underwater. So you will have an erosion surface because it's an unconformity. That is why I'm drawing it macam gini lah. Goes up and down, right? So just marks an unconformity. In some places, the unconformity can be very deep, and in some places it's much shallower. Okay. Now notice here, my definition for sequence boundary is subaerial unconformity plus correlative conformity. So on land, it is an unconformity. But let's say this is your shoreline. Kat sini sempadan di antara darat dengan laut. This is your pesisir pantai, shoreline. So what happens to the unconformity when you go underwater? It becomes a conformable surface. It's no longer an erosional subaerial erosion surface anymore. Bukan disebabkan oleh hakisan di bawah di atas permukaan bumi. So it's more of a straight line being drawn here. And this surface here can be correlated. It is equivalent to the subaerial unconformity. So we say it is correlative. Kita boleh sambung antara ini dengan ini. And it is a conformity. So it is the opposite of an unconformity. Ini bukan unconformity. There is no major stratigraphic gap. Alright. So the correlative conformity, usually abbreviated CC, biasanya kita tak CC sini, is the marine portion of the sequence boundary. Right? This is going to be your ancient seafloor, your paleo seafloor at the end of forced regression, and there was no subaerial erosion. Right? So far, okay. Any questions? So we just look at sequence boundaries first. Kita tengok sequence boundary dahulu. So it is a subaerial unconformity plus a correlative conformity. If no questions, I'm going to continue. All right. Okay, so the sequence boundary marks the base and top of a sequence. Obviously, kan, kita kata sempadan di antara sequence. So it's going to be marking the base and top of a sequence. Okay, so this package here, marked by the arrows here, which is going to be a single sequence. So at the base, there's going to be a sequence boundary, and also at the top, there's going to be a sequence boundary. All right. Now, let's just have a brief look at how you get the development of a sequence boundary. Okay. So, let's start with a high stand phase. So, during high stand, right, relative sea level is very high. Aras selalu amat tinggi. So, this is your relative sea level during time 1, during the HST. Right. So, but sediments, but it is slowing down. Because of that, you get aggradation followed by progradation. So you get development of a delta on the shoreline, and in this case, it is prograding. It's shallowing upwards. See, shoreline was here, followed by here, followed by here, until it reaches a very it's still rising, but it's rising very slowly. And further landward, you get an alluvial plain, ada sungai kat belah daratan. Ya. Okay. So later on, sea level starts to go down really fast. This is during the early low stand phase or the falling stage systems track, right? So sea level was here before during the HST, kat atas sini, time 1. Now, sea level falls to here, sea level time 2. Okay, so what happens? The part which is here, which was sea level previous here, is now fallen down here. Parts which are much higher compared to sea level on land will be eroded. Semua ni akan dihakis. So be eroded, and that is why you get an unconformity. So you'll notice in many cases, the upper part of the HST is most of the time missing in most preserved sequences. In some cases, the HST is completely missing because of deep erosion. Okay, we'll talk about that later on. So you get an erosion surface on land. In some cases, in some places, the erosion is going to be very deep, and this usually happens when you have a river. So rivers are where flow is concentrated, water flow is concentrated. So erosion can be much deeper. You get an incised valley. Okay, dapat satu lembah sungai yang amat dalam. Okay, and that is because of water flowing very fast in your river valleys. Okay, away from your river valleys, you still get erosion, but not that deep. Okay, so there's still a subaerial unconformity. And seaward of the shoreline is now here, you get still progradation, but shoreline is now downstepping, goes down, right? So it is forced regression. Okay? And later on, you have a delta is moving further and further downwards, downstepping, forced regressive sedimentary package. Okay? And further seaward here is not an unconformity, it is a correlative conformity. Okay, no unconformity here, but it can be traced. All right. So that is why you get an unconformity. That is your sequence boundary. But later on, after the forced regression, you start to get sea level rising again, but it rises very slow, kan? Mula-mula slow. So it is the low stand phase. And during low stand phase, because of the slow rise in the relative sea level, you start to get accommodation space being created. Ada ruang di mana kita boleh isi. So during the end of forced regression, sea level was at time 2. Now it's slowly rising and bergerak ke atas, so slow during the low stand reaches time 3. So your valleys will now be filled in with fluvial deposits and they will be aggrading. Dia membina ke atas, so it is aggradation. And in the marine area, you get continued delta progradation. So it's going from progradation now to aggradation nanti kemudian. All right. So you have high stand at the bottom. Some parts of a high stand has been eroded, hilang, missing forever. then you start to get aggradation and progression of more sediment on top of your sequence boundary. Okay, so that's how you get the development of a sequence boundary. So notice something, and notice a contact here. It is pro-delta, unconformity, fluvial deposition. So just by looking at the pattern, we know that this is forced regression, because we have what is called an abrupt shift in fasces. Normally, in a normal regression, it's going to be like this, kan? Oh, it's going to be gradually showing upwards gitu. Pro-delta, delta front, fluvial. But here, it is abrupt. Pro-delta, boom. Suddenly, it just goes into fluvial. Where's the delta front? You start to think. And if you find that in an outcrop, or if you find that in your well logs or cores, right? One interpretation is that you have an unconformity, because there is a sharp and abrupt shift in the fasces. And the fasces is actually going from deeper to much shallower. Okay? So that's how you identify the sequence boundary. Show you examples now of a sequence boundary, right? All of you guys did the sedimentology filtrate virtually ke followed me to Perlis? I can't remember.
For me, I went for virtual field trip.
Okay, so you guys went for the virtual field trip, then. So you should know this outcrop. This is the Kampung Gangara outcrop in Labuan. You have a 3D model of it. I think you also have the photo in your slides, again. So yeah, let's construct the premise first. We have strata made up of clastic deposits. Darker colored here is shale. Lighter colored is sandstones and conglomerates. Okay, and you can see beds, and we are dipping towards your left. Yeah? Okay, and you have humans for scale here. It'll be something like 1.7, 1.8 meters tall here. So we have an interpreted sequence boundary at this outcrop. Okay, so let's look why do we think that this is a sequence boundary. First, a sequence boundary must be a surface of erosion or non-deposition. And here we have a sharp surface going from shale here to conglomerates and sandstone here. And it is going up and down. So it is an erosional surface in this case. And it was created during relative sea level fall, and created by subaerial processes, things like fluvial incision, sediment bypass, and the creation of soils. And it separates genetically unrelated strata. So it just means that the layers below and above the unconformity, the sequence boundary, are not conformable. They are from different packages of sediments, from very different deposition settings. Yeah? And the sequence boundary marks an abrupt basinward fasces shift. So we have a sharp surface, it is erosional. It marks an abrupt basinward fasces shift. Bawah ni marine, goes here, boom, fluvial. And you start thinking, hey, where's the delta front? It's not here. It's just marine, everything. So that is what is meant by abrupt, tiba-tiba je. And you have a fasces shift, marine to fluvial. And it is basinward. It's not going from deeper, it's not going from shallow to deep, but going from deep to shallow, right? So once you get that, that is going to be a subaerial unconformity interpreted, and also a sequence boundary. Okay. So in this case, you have marine shale at the bottom and fluvial sandstones conglomerates at the top. And this has been interpreted as a very important unconformity in Borneo. Okay, I also mentioned the term incise valleys to you. An incise valley is also part of your sequence boundary. It doesn't happen everywhere. Dia tak terbentuk semua tempat. It happens when you have a river valley. And when you have a river valley, a lot of the water is going to be concentrated inside the river valley. And the other places you don't have much rivers, not much erosion. But when you have a river valley, the river will cut deeper and deeper into the shelf. So this is what is called an incised valley. Ada lembah and terpotong. And marks a large base level fall, and the rivers incise into the substrate. And the fluvial valleys become a zone of erosion, of course, and sediment bypass. What is meant by sediment bypass? It's basically a highway. If you have water flowing through here from the land to the sea, a lot of the sediment is not going to be trapped here. Dia tak akan terperangkap sini. Most of it will just bypass it. Dia lalu je and go straight to the sea and becomes dumped as part of the low stand delta. And also, yeah, part of the low stand delta and the falling state system strikes delta. Okay. So fluvial valleys become zones of erosion and sediment bypass. What about the areas away from the river valleys here? What's happening here? Now, these areas we call interfluves. Inter between fluve, rivers, di antara sungai lah. Okay. And here, it's mostly non-erosion, but you can still get, it's a combination between non-erosion and erosion. And you also have lots of soil forming. This soil weathering is occurring here because there is subaerial exposure. Yeah, dulu hawa sini ya. Yeah, your incision can be very significant. It can be more than 20 to 30 meters deep, this is valley incision here. So you get a high relief sequence boundary forming within inside the fluvial valleys. So here you have river incision, it could be 20, 30 meters deep, but it's much shallower along the higher interfluve areas. And mostly you get a lot of soil being developed here. Okay, so adjacent interfluves, you get zones of non-deposition, an age gap, of course, because no deposition is there, and thick soil formation. At the base of rivers, you get an unconformity and a time hiatus, a very big gap, because a lot of sediment is missing now. Top part of the deltas here has already been destroyed. Okay? Other things you get associated with the incised valleys are subordinate tributary feeders. I'll show you pictures of tributary feeders after this. Okay. And then it's going to be overlain by deposits of the low stand later on. So examples of photos here, aerial photos from incised valleys. You can still see in the modern times here. You can still see today. So this is a map view, and around here you see the interfluves and the deeper cutted parts here with significant relief, right? So this is your river valley, your incised valley. Sea level has fallen, so you get this incision in the middle. And there's still a river with low sinuosity flowing in the middle, right? But you also see these branching tributary feeder systems here. So erosion is also cutting towards the side here. You can have smaller rivers feeding into the larger river also, right? So you get these tributary feeder valleys here. So that is a hallmark, ni satu petanda that you have an incised valley, with dendritic tributary systems. Okay, they are much smaller compared to the main incised valley. So this is another incised valley. We're looking at it from a different angle now. It's not plan view. So you see the main valley axis here with a meandering river system in the middle. Okay. So meanders, lots of rivers, floodplains in between. But you have this deep erosion surface here. Okay. So this is your incised valley. And you also have the deeply cut, smaller tributary valleys along the side. And that is characteristic of incised valleys. And incised valleys happen because you have forced regression due to relative sea level fall. Okay, a better photo lah. Now I've labeled it, tract valley and tributary valleys. So you have lots of different characteristics, lots of criteria in order to identify incised valleys. They are listed here lah. So in this example here, you have multiple feeder tributary valleys, the main incised trunk valley. And also you have the presence of a widespread fluvial erosion surface characterized by significant relief, greater than 15 to 20 meters. Anomalously well-developed paleosoils, ancient soil, tanah lama, on interfluves between incised valleys. Soils being developed here in the interfluves. Okay. So you can read the list, but I'll just show you examples of the criteria in the next few slides. Now we are looking at insize values also, but in cross section. Ini kelihatan rentas. We're not looking at it from the top, but from the side. This is an outcrop exposure. So these are ancient insize values. So let's see what you have, right? So notice here you have the white color here is sandstone. The gray color here is mostly mudstone. You still see some thin layers of sandstone in between the lighter color parts here, right? But notice this lens of sandstone here. So this is an incised valley fill. You have an unconformity at the bottom, which is very irregular. It is bowl-shaped. It goes up here, again, like a channel, right? But it's mainly made up of lots and lots of channels, not just a single channel. It's amalgamated. Erosion. We know that there's erosion because if you trace the layers here, they become cut. Itu potong kat tepi ni. And that's called truncation, right? And it's marked by these arrows here. So this is going to be an incised valley. The bottom part might be high stand here, followed by low stand fluvial deposits here. There's another incised valley at the bottom here. It's much more extensive. An erosional surface at the base is going to be your sequence boundary, and your sandstones at the top, which are fluvial, followed by marine. So this is going to be the incised valley fill. Okay. So you see several characteristics of incised valleys here. First, anomalously thick channel deposits. Quite thick here. This is going to be something like 30, 40 meters. Those are trees. Multi-story fill of fluvial channels. It's more than one channel deposit. It's not a single channel deposit. It's stacked on top of each other. You have the presence of multiple channel fill deposits clustered within a relatively small vertical section. So it just means the same thing as it's amalgamated. But channel or valley fill is significantly younger than the underlying deposits. So they're older here and younger here. And there's going to be an age gap. Maybe 1 million years is gone, 100,000 years. And we need fossils to determine that. What else? Channel and valley fill usually is characterized by lithology distinctly different from underlying deposits. You have marine shale at the bottom and fluvial deposits at the top. So it's distinctly different. Hang it up, and I need to admit people into the class here. Okay. Any questions so far? Because kita berhenti, saya tanya dulu. Any questions? 1,000, 2, 1,000, 3, 1,000. Okay, so if there are no questions, let's move on. Okay. Another example of an incised valley. So we've looked at how incised valleys look like at outcrop, how they look like in a modern environment, right? You have low sea levels, you can actually see the river valleys from above in aerial view. How do they look like in a seismic section? We've learned about seismic reflections in the previous practical. Now let's look at how they look like. So this is what you get. So in this case, the sequence boundary has already been marked. This is the dashed line representing the sequence boundary here. Straight, then it goes downwards, upwards again, downwards again. So you have an irregular surface and it is erosional. We know it is erosional. Look at this. If you trace a layer here, seismic reflections here representing contrast in rock character, right? So you get different. Because of that, you get reflections representing acoustic impedance. So you can say, in this case, we're interpreting that these represent sedimentary layers. So you see, it's almost horizontal, it goes here, but it stops here. Here, you get a different kind of seismic signature, but it's more chaotic, right? It's more curving, lots of different kinds of geometry. It's no longer straight. And that happens because there is erosion. It's truncation. The layers have been cut. But the layers here can actually be traced on the other side of this cut here. Yeah? This is going to be the same age. And on the other side also, you can also trace it here because of the principle of lateral continuity. Right? So that's going to be, these are incised valleys. That's one incised valley here, and this is another incised valley. Okay, so how do we know that this is an incised valley? Well, these features here have several characteristics which are consistent with an insights value interpretation. One, you have an anomalously thick channel fill deposit. It's probably something like 30, 40 meters thick. And the channel fill deposit is multi-story again, lots of channels on top of each other. You have channelized deposits that hang from the same stratigraphic horizon in most localities. So you have this stratigraphic horizon, and then you have these incisions, but they are still hanging from this horizon here. Multiple channel fill deposits, I've seen that. It's going to be significantly younger than the underlying deposits here. We need to prove that with fossils. Channel valley fill characterized by lithology distinctly different from the underlying deposit. Well, here we don't see the rocks, but looking from the seismic character here, it's very different, right? This is more straight and continuous. This is more chaotic, and it's going everywhere here. So most likely it's a different kind of lithology. So mark here is your SB. Okay. So yeah, in cartoon shape, the concept is like this, right? You have deep incision, so you get a thicker deposit of low stands here. And away from the incised valley is very low degree of deposition, maybe just a very thin layer of soil or floodplain deposits, or maybe nothing is preserved. So here you have thick low stand, here maybe no low stand being deposited. So you go from HST, atas here, let's say what, it might be TST or HST, and it just goes to another sequence without any LST being preserved. That happens in the interfluve areas. So that's one thing to remember. In an incised valley, you would expect to have low stand deposits on top of your sequence boundary. But away from it, no low stand will be preserved. It's missing. You just go from lots of parallel sequences to more parallel sequences at the top, but different system strength. So it's going to be very hard to identify a sequence boundary in the interfluves. It's much easier to do it in incised valleys. So example now in core, well, it's the same thing, right? So you have a gamma ray log at the side here, in gamma ray. We learned about gamma rays in the previous class. So the gamma ray shows that you have a shaly and sandy interval at the bottom, but then abrupt change to a blocky sand at the top here, right? And there's a cold spike here at the top. And then the person here has already sampled the sedimentary succession, taking a cylindrical core sample and brought it up to the surface and looked at the features here. And this is what we get. We make a sedimentary log. So going from, at the bottom here, deltaic marine shale, this part here, gray in color, right? So this is going to be the part here. And this is abruptly overlain by fluvial deposits, sandstone with cross bedding, right? So this is your sequence boundary now. Abrupt shift, delta front to fluvial. You might say, hey, bukan itu, isn't that normal, right? Normal regression. Well, let's say this is still delta front, but the upper part of the delta front should have things like mouth bars and so on, yeah? But it's not there, it's missing, has been eroded into. And the surface is quite sharp. Yeah? It's not quite sharp, the surface is sharp. So that's an erosional surface. So in this case, we are interpreting this as a sequence boundary. Okay, so just to show you again, I need to emphasize this. Inside the incised valleys, you get a perfect pattern to the sequence. High stand, low stand, TST, HST, and then followed by another sequence at the top. Yeah. But on the interfluves, you get a different kind of pattern. High stand, TST terus, no low stand, right? Because you are away from the rivers, so there's not much accommodation space here. It's highland, right? So no river deposits at all. So it's going to be hard to identify the sequence boundary, but there are certain clues. Maybe you have rootlets here and development of a soil, right? So telling you that it was subaerially exposed. And there is also, you can also use biostratigraphy. There is an age gap. So you can use these kinds of things to identify a sequence boundary on the interfluves, right? That's okay. Any questions? Okay.
Tak ada, Doktor.
All right. No questions. Let's go to the next kind of surface, which is called the transgressive surface. It is, one thing you need to remember, it is just a type of marine flooding surface. It's also a marine flooding surface. But it is the first flooding surface to appear during the TST. So it marks the boundary, the base of your TST. Separates the LST from the TST. And it marks the onset of transgression. So go from low stand here, it's fluvial. And it changes into marine here, let's say. Maybe it's estuarine here. So that change is marked by a surface. It's called the transgressive surface. Okay. Another thing, in incised valleys, it's going to be easy to separate between SB and TS. But on the interflows, what happens is that because you don't have any low stand, but two surfaces merge, dia bergabung di satu. There'll be an SB plus a TS on the interflows. So show you an example in outcrop, how does a TS look like? So this orangey to reddish colored deposit at the bottom here, it is a fluvial sandstone to conglomerate. Bottom. Beds are almost horizontal, isn't it? And above it is a shore-face sandstone, very clean and very light colored sandstone here with Humke cross stratification, low angle cross stratification, and parallel stratification. So this is a shore-face deposit. Now this is very unusual. Why you get fluvial then followed by shore-face at the top? So this is going to be marked by an abrupt shift in facies. It's going from shallower to deeper now, the other way around compared to a sequence boundary. So this is your sequence. This is going to be your TS. This is right here. From fluvial to shore face, from shallow to marine. Okay. One thing to remember also, the TS doesn't have to be at the top of the incised valley. It can also happen inside the incised valley. Yeah? Fluvial sini LST. Then you have a transgressive surface. Atas there you have the estuary deposits. It's more brackish water, tidal things, right? Before going into fully marine at the top. Okay. So that is the boundary between fluvial and estuary here. This is going to be a transgressive surface. LST, TST, followed by an HST at the top here. Okay. Don't worry, we're going to do practicals later on how to identify the different types of key stratigraphic surfaces. One more key surface that you need to know is the MFS, the maximum flooding surface. You need to really know this one because it's the easiest surface to identify in subsurface data. If you are working with things like well logs or with seismic, the MFS is very easy to identify. Sequence boundaries are very dramatic. Mungkin lagi senang jumpa sequence boundary. No, it's easier to find an MFS rather than a sequence boundary most of the time. So let's look at what is an MFS. It is a surface at the time of maximum transgression of the shelf. Okay, so that's the MFS here. It goes up and down in this case. And it separates the TST below, one TST, retrograde, R, going backwards. And the overlying HST is going from A-grade to prograde. It's a boundary between the two system stacks, TST, HST. And most of the time, it's just very thin. It's just I'm not going to go too much into the theory part, into the details, but yeah, most of the time the deposits associated with the MFS is very thin. It represents long periods of time, even though it's very thin, because during the maximum flying surface here, the shoreline is the furthest away from the sea. Dulu darat pesisir pantai kat sini, tapi dia bergerak sini, further and further left. Let's say your shoreline is here, right? If you have any sediments, it's going to be trapped mostly along the coast as deltas. And further in the deeper parts, not much deposition is happening. It's mostly just suspension, clay particles falling down. And that can happen for a long period of time, hundreds of thousands of years, nothing is happening. So even though the time period that has passed is very long, but the deposit can be very thin. Nipis here. Well, lots of different fossils at different ages, it's concentrated together. It's what we call a condensed section. Now, another thing about MFS surfaces, the age of the surface is different in different parts. it's going to be much older here and much younger further landward. Why? Sebab dulunya air laut sampai sini je. So deposit sini umur dia ini yang paling awal. Earlier deposition was here because sea level was only up to here. But then sea level rose, you get more deposition on this part here. Sea level rose, more deposition here. So your deposits become younger and younger and younger on the maximum flooding surface. Condensed sections associated with the MFS are dominated by fine grain, pelagic and hemipelagic deposits, mostly just a lot of clay being deposited, and also with fossil plankton, which has fallen down to suspension after they died. Okay, so like I said, the MFS is the easiest surface to identify. How do you identify MFS? It is going to be, if you're working with well logs, it's going to be the shaliest part of the sequence. Okay, MFS, shaliest part of the sequence. And again, the reason is this, because it's going to be very far away from the land. Most of the time, it's just a lot of suspension fallout, hemipelagic and pelagic deposits. So it's only the shaliest part, not much in terms of sand. Sand tak sampai, jauh sangat. So if you have a gamma ray curve here, and most of the time, the MFS is going to be the shaliest part. Here is the highest gamma is in this area here. It's going to be somewhere here. Here, not really, because it's going to be low gamma, it's going to be sandy, right? So you can already interpret it here. Maybe here is low stand, sandy. TST, where you get shalier and shalier go further upwards. And that's the shaliest going to be the MFS, followed by an HST, which goes from shaly to muddier now. So that's a nice cycle. That's a single sequence there. And you can easily identify the MFS here. But yeah, you get different kinds of patterns to your gamma ray depending on where you are and on the basin. Maybe on land it looks like this. Maybe further seaward it looks like something like this. Fluvial, blocky sands at the bottom, low gamma, slightly higher gamma here, and here it's going to be subtle. If you want to identify the MFS, it's going to be a little bit subtler because it's overall the package is sandy. It's susah sikit nak kenal. And you might use things like core to determine that there is a change in fasces, and that's the deepest fasces is in the middle here, sini ke. Or you can use fossils ke. Yeah, this is another example. Further in the shallow marine part, you find the shaliest part here. It's going to be easy to find here. MFS here. MFS is the shaliest part of the sequence, high concentration of organic matter and radioactive elements. So you get the highest gamma ray readings, and it's going to be the easiest surface to identify for doing sequence stratigraphy. Okay, that's how you identify MFS in well logs. It's also easy to identify MFS in seismic if you're working in the shallow parts of the basin, yeah, coastal deposits gitu. Because the MFS is also called a downlap surface. Why do we call it a downlap surface? Well, we have these stratoterminations. Notice, you can see that these layers are dipping, right? Forming this curving epsilon shape. It's sigmoidal, sorry, sigmoidal shape. Goes down here. And this represents delta clinoforms. And the delta is prograding from right to left. Delta you bergerak daripada kanan ke kiri. Yeah. So you can actually imagine this was previously delta plane. You have a delta front, you to delta. We have packages and you have progradation towards the left. And now, if you follow these layers, these are your clinoforms here. Okay? So it goes from straight here, sloping, and the angle of dip is decreasing, become more and more gentle. Go for the seaward gini. And then it meets with the surface here. That is a downlap, a stratotermination called a downlap. And we'll learn about downlaps later on also during the practical. Now, this surface, where all these layers go down and meets the surface here, this is a downlap surface, and most of the time, this is going to represent your MFS. And that is because you have TST, retrogradation, followed by progradation, and the progradation will be happening on top of the MFS. That is why it is touching the MFS here. Okay. So yeah, if I zoom in onto this part here, but this is the other way around. The progression is now towards the right. You have this seafloor here, surface here. It's roughly horizontal, right? See? And then you have this curving shape, this dipping surface here, part of a delta, and it meets this surface here. So this line here, which has been marked black here, is the MFS. Okay, it's already 8:50. That's the final slide. Any questions before we end? Ada? All right. So if there are no further questions, I will meet group number 2 on Wednesday. Okay. That's it for today. See you on Wednesday. Thanks.
Doctor.
Thank you, Doctor.